Good day, everyone. Welcome to ME154, and this is the last lecture for friction elements. So, for the first three lectures, we've tackled the force analysis and the basically just the force and everything that deals with just the basic stress performance of most friction elements. Now we're going to look into more on the energy side of things, and as a consequence, also be examining some strategies to mitigate some of those extra considerations as well as the materials used in friction elements. So to get right to it, the energy transfer in clutch and brakes, um, they're not particularly, let's just say, they're not super remarkable under steady state conditions, but they are interesting when it comes to the transient conditions, especially for brakes. Now, before we go into brakes, we have to discuss clutches first, and this is the extra thing that we need to talk about. So for clutches, there are actually two types of clutches. The first one is the positive contact clutch. Now, the positive contact clutch just means that the way of transferring torque from one end of a drivetrain to another is done through interlocking parts. Now, there is a pro and a con for this kind of setup. For the first pro is that there's no slippage. There's no chance for the other side to slip away from the rotation of the other side. This is common when you want performance or you want heavy duty loads to be applied in your drivetrain. However, you do need what we call synchronizers to avoid shock loading. As you can kind of expect, um, for most of these positive contact clutches, like for example, this dog clutch or this tooth clutch, uh, if you if you mate these two sides of the clutch at the wrong orientation, you would get a lot of shock on either side of the system. So that is the main weakness of this kind of clutch. And you kind of have to have some system in order to ensure that these pieces or sides of the clutch won't do anything, won't wear themselves out essentially. If you can figure that out, you end up with a clutch that wears that doesn't wear as much, that wear has a longer life, and essentially doesn't really have most of the drawbacks that we have to address for the elements that we discussed for for the previous three lectures. So now we go on to the types of clutches that we have been discussing for the longest time, which is friction clutch. So you kind of rely here on the element of friction. So essentially, um, you're kind of hoping that if you touch this side of the clutch while it's rotating, the other side will start to just join in or synchronize with the first, with the rotating element. The weakness with this is that there is slippage, especially upon first contact. There is slippage. However, there is also a terrible amount of wear. So for friction clutches and friction brakes, there are mechanisms to ensure that this kind of wear is kind of compensated for, whether it's through part replacement or some other little mechanism to ensure that there is as much that to ensure that you can get as much performance out of this kind of clutch as you possibly can. Now, the benefit of this is that while it does generate heat while it's synchronizing, it does produce minimal shock when you touch one end of the clutch to another. So for positive contact clutch, like you have to be you have to time it just right to avoid incredible shocks on your system. But for the friction clutch, because the other side is not forced to immediately follow one end of the rotating side, it doesn't experience as much shock when it's trying to synchronize. So most of our discussion, succeeding discussion, will be on the friction clutch side. So for clutches, at least, the rotation does not transfer immediately. So this is true for friction clutches. So while there is some rotational energy being transferred at the start, there is a lot of heat that is being dissipated through friction. And this is also true for brakes. In fact, brakes actually rely on friction to dissipate all that energy that is in the rotation. So you really need friction for this part. Now, when it comes to clutches, we do have a very simple model. We use the basic dynamic moment expression for a rotating body. So for physics and NSI 12, I believe this is I alpha. But right now I'm using ME 160 symbols here. So J sub M1 is essentially just I sub 1 in NSI 12 terms. Theta double dot is just the angular acceleration alpha. And both sides are kind of experiencing a different polarities of torque. Now, these vectors here are just vectors for the rotation, not the torque itself. So hence they're in the same direction. Now, for each of these parts of the clutch, they experience a particular angular velocity. Now, any point in the time, they may or may not be synchronized just yet. So how did we get this? We actually divided the entire equation here by the mass inertia, and then we integrated it. So this extra term here is actually the initial angular velocity of either side of these clutches before the contact was initiated. So now, what's important here is that we have to be able to define some kind of relative velocity between these two sides of the clutch. And we can get that by just taking the difference out of them. So why is it important? Is because we know that we get synchronization when the relative velocity or the difference between the angular velocities of those two parts reduces to zero. And for Budinas and Nisbet, they didn't really label this particular quantity T sub 1. This is essentially the solution if you equate this equation to zero. Equate this equation to zero. Wow, okay. So if this relative velocity zeroes out, this T sub 1 will function as a solution. So you might, I suppose you can call this the synchronizing time. For automotive terms, I believe they call this the shift time. But for our case, we are looking at things in the general perspective. So maybe shift time is too specific for our case, but you can just call it whatever. So for this lecture, I'll just call this T sub 1 or sync time. So now, as I've discussed in the previous slides, there is energy leakage while the clutch is synchronizing, and that energy leak can be expressed through a torque times the relative velocity function. So this is actually a function of power, and this is just t times essentially omega. So yeah, t times omega. Now if you plot this and you follow along the trend of the curve until synchronization, this area under the curve is actually the total energy dissipated. So in order to get this total quantity, we take the integral of this energy dissipation function from time equals 0 to the sync time, t sub 1. So that the energy that is dissipated during synchronization is actually this letter E here. So is it a very mouthful? Yeah, it is a mouthful. If you want to simplify this equation, you can use Shigley's form, which is just I sub 1, I sub 2 over I sub 1 plus I sub 2. And this one is omega 1 minus omega 2 squared. Now, since we're mostly basing our analysis on Shigley's work, it does use British units. So you have to be careful. So I'm just gonna define some of the variables that Shigley uses at this point. So for some reason, even though it's technically the mass, it Shigley uses the symbol capital W. I presume it's because the unit that Shigley is using is pound mass. Pound mass is technically mass, but it's kind of like the reverse of kilogram force. So yeah, I suppose Shigley just wants to make a distinction for, okay, so this is a mass term, but it's in pound mass. So if you can recall, the British system actually has a unique um, quantity for mass, which is the slug. But since the slug is so rare in use, sometimes people just say, okay, let's just use the mass equivalent of 1 pound. So that's where pound mass comes from. And that is also the source of the units for mass inertia. And because we're kind of basing off of the pound, the dynamics of the units is kind of different. So just be careful about that. When we use the British system, we end up with an energy term that has the units of inch pound force, which is essentially just distance times force. Now, to take note, the British unit or the British system has a different preferred energy unit for thermal energy. So, for mechanical energy, it likes inch pound force or foot pound force or something of that caliber. But when it comes to heat, it prefers the British thermal unit. And when we want to convert inch pound force to British thermal units, here is the conversion factor. So why should we discuss this? It's because Shigley is using British units when it's discussing this. All right. Let's talk about energy dissipation. Now, when it comes to energy dissipation, this will now be mostly on brakes. And the reason why we want to focus on brakes is that brakes actually experience highly thermally intense environments during their operation. So we're going to take the most extreme kind of brake, which is the aircraft disc brake. So these kinds of brakes, they're kind of hidden within the landing gear of commercial aircraft. And the graph here represents the two temperature readouts for the disc brakes during regular operation. So there is no indication of what this x-axis is. We believe it's in minutes. So it's time versus temperature. And what you notice is that a a regular operation consists of multiple flights. So there is regular takeoff, there is just chill flight, and then there's landing, taxi in, and then you fly out, then you fly in again, over and over again. And although there's a lot of data here, there's also a difference. There's an indicated temperature and there's a disk temperature. I believe the disk temperature is closer to the actual one that the brakes feel. So what I want you to notice is that for the duration of a single regular operation, the temperature of the brakes almost never dips below 100 degrees Celsius. So we have to point this out. The brakes after the first flight regularly do not go down below water boiling temperature. And what is the maximum temperature that these disc brakes experience? Around 700 degrees Celsius, maybe above 8, maybe around 800 degrees Celsius even. So this is a problem because if you can recall the very first material characteristics lectures that we've had, the eutectoid temperature of plain carbon steel is around 700 degrees Celsius. If you were to use regular steel on this kind of brake system, the brakes will change material properties mid-flight. And that is insane. That is insane to think about. So you can't use plain carbon steel for this kind of setup. So you require a different kind of material for these heavy duty thermally intense applications. But what we'll discuss is, okay, if the materials are essentially just right for the application, let's look for ways to mitigate any disastrous environmental conditions that these materials can encounter. And we can do that by figuring out what kind of heat dissipation strategies we want to adopt. So when we go to heat dissipation, we do have two regular expressions. So I believe you're familiar with this. This is just the heat transfer expression, but in British. So this this is energy in British thermal units. Again, W is just pound mass. So if you want to take care of the units, so this is it. This is the units, and this is the equivalent in SI. Now there is a much more appropriate model for the heat transfer for brakes, and that is the transient form. So I hope this is familiar to you. This transient form also has a partner, which is the uh, heat dissipation equation, but in this form, which is UA delta T, or for this case, it's the H with the stroke, A times delta T. So these are the um, meanings of the variables. And again, please be careful because this is in British units. The relationship between the units that appear on the unit side is a little different. So especially for the overall heat transfer coefficient, please be careful about this. All right. So this kind of form of equation, this is kind of associated with convection. But is it really just convection? So I believe the H with the stroke kind of points out, okay, so this is probably not just convection. In other books like Sengel, I believe we would rather use the capital letter U. So it would be U, A delta T. And for brakes themselves, there are two modes of heat dissipation. It dissipates energy through radiation, of course. So the disk heats up and it just electromagnetically releases some of that heat. The other one is the forced convection heat transfer. So, okay, you might be thinking, okay, wait, brakes and the forced convection heat transfer. So, you kind of might imagine, okay, where's the fan? Where is the forced draft fan blowing over the brakes in my car or in my motorcycle? So for cars, at least they are well hidden, but there are usually two strategies for cars. So the first one is just by having bumper vents. So if you take a look at your car or your family's car, there are vents to the side of your bumper, and those vents should direct air into the brake region or the brake space of your car, especially the front brakes. So air, because your car is moving really fast, is being forced into this space, thus causing forced ventilation. Now the other method is, especially if you find that you're kind of using your car in a very intense manner, you can have custom brake ducts. So instead of just allowing air to find its way into the brake space, you actually create an enclosed system such that the air coming from the front is forced directly into the brake pads or the brake discs. So this can come in custom, but I believe supercars already come with a more specialized looking brake duct. Now, if you have a normal car, I believe you can customize it to have this kind of setup. Essentially, okay, so the air coming from the front just enters in, and 100% of that air is actually blown into the discs. It's kind of insane. There is reason for it though. So, like for example, this custom brake duct by Rob Robinette was actually undertaken because some of his brake parts melted off. Like, this is a normal car, and while this person was driving, some of the parts started melting off, and that's kind of crazy. So, yeah, uh, ventilation is important. Now, is it only for cars? For motorcycles and bicycles, they are open air, so they are kind of partially exposed to some forced ventilation, but others might want to take it a little further. So this is kind of a cheap duct. No, not this is not cheap actually. This is a very expensive I believe, a carbon fiber layered shape in order to funnel air from the front into the caliper region of your disc brake so that you can get a much more efficient heat dissipation. All right. So for the H stroke is actually composed of two heat transfer coefficients. We have a radiative heat transfer coefficient and we have a convective heat transfer coefficient. Wait, why is the radiation heat transfer component not epsilon why is it not epsilon sigma t raised to 4? Sometimes it just happens. Let's just say sometimes it just happens. Like every everything about heat transfer that is not solid, basically fluid heat transfer, you can kind of boil down to UA delta T somehow for some reason. So you can kind of just skip the steps. Just imagine that it is kind of convective. Now, what you notice here is that your convective heat transfer term here is mediated by this multiplication factor. This multiplication factor is linked to the velocity of the mean air coming into the brakes. So when you're looking for heat transfer coefficients, what you want to look out for is the temperature difference of the brake versus the ambient. So once you've located, let's say, the temperature difference of my brake versus the ambient at any moment is 200 degrees Fahrenheit. So at 200 degrees Fahrenheit, I just match it to the curve that I'm looking for. So let's say convective heat transfer. All right, so convective heat transfer, and I just match it to the vertical axis. Now be careful of this vertical axis. If you see here, all these terms are multiplied by 10 raised to negative 6. So you have to add that back in when you're using this the values from here. Same with the multiplying factor. Find the mean velocity of the forced air, and then where it meets the curve, that is your multiplying factor. So when you're modeling actual braking conditions, it can be difficult. So like for example, if we go back here, things kind of change depending on the minutia of the performance. One cycle of a single operation might be a little different from the others. Like for example, the first flight conditions, the first flight operation for this aircraft disc brake is different from the second. The second is slightly different from the third, and so is the fourth, just a little bit. So to make things simpler, we are going to assume that the periods of brake activation and brake cooldown are kind of the same. So you have a repeating pattern of activate the brake, then let it cool down, then activate the brake, let it cool down. If you plot it on a time curve, it kind of looks like this. So how would you think of this kind of curve? So imagine that the vertical spikes are the immediate application of the brake. So you press on the brake and the brake heats up to its maximum temperature and then you let go. And once you let go, the brake dissipates some of that heat, loses that energy, and then you press the brakes again instantaneously. Boom, the temperature rises again to Tmax. And then it falls down slowly again at the same interval. And when you have this concerto of, okay, once I reach this minimum temperature by this T sub 1 sync time, I press the brakes again to maximum temperature and so on and so on. We can be able to uh, kind of figure out some properties of the heat dissipation of the brakes. And using this model, um, we can figure out, we can solve it at our level. So the difference between brakes and clutches is that one of the sides of the brakes is not rotating. So one element has zero mass inertia. One element has zero angular velocity, and that gives you an energy dissipation equation of just this. So the omegas here are now adjusted. Omega naught is the initial. velocity of the disk or the shaft that you're trying to stop, and the final velocity is whatever your end goal is. Now, the temperature rise is just MC delta T, derived from MC delta T. Yep, that's it. So this delta T is actually T max minus T min. Right. Now, for the transient side of things, your numerator side is now the difference between the minimum temperature and the ambient, while the denominator is the maximum temperature difference to the ambient. Beta here is just kind of the shortcut. It's the inverse time constant. So it's just h with a stroke times a over mass, which is in W here, times Cp. If you rearrange this equation, you will get an expression for the maximum temperature. So where did T min go? It actually went to delta T. So you have to remember delta T is actually T max minus T min. So yeah, that's where the minimum temperature disappeared to in this side. So these are the four equations that you want to look out for when we're solving for the heat dissipation issue of certain breaks. And given that, let's look at an example. So I'm gonna read through this example. So to bring a shaft spinning at 250 RPM to a stop, a caliper brake, so which is basically another word for a disc brake, is activated 24 times in a single hour. Now, the brake ducts provide an average of 25 feet per second of cooling air. So, the disc is 6 inches in diameter and it's a fourth of an inch thick, and it has a particular density. And its equivalent mass inertia is 289 pound mass inch second. Now, the caliper's pads are made of dry sintered metal, and the surface that is being activated during the braking period is around 50 inches squared. So, we're tasked with finding the maximum temperature and the minimum temperature during a regular braking operation. So, as a footnote, the ambient conditions are 70 degrees Fahrenheit. So again, we're kind of tasked with finding the peak temperature and the minimum temperature. So how do we go about this? So perhaps we can start with a description of the brake use. So the brake use given to us here is that the caliper brake is activated 24 times in a single hour. So from here, actually, we can get our T sub 1, our sync time. Our sync time is actually 1 hour divided by 24 times. So 1 hour divided by 24 times. So that is 150 seconds. One period of a sudden spike in temperature and then a slow decrease is 150 seconds. That is what this T sub 1 means. And now, the issue with this problem is that we have no idea what the T max is, we have no idea what the T min is, so we have to resort to iteration. So for iteration, we have to keep in mind the next step of our solution. So in order to make anything possible for this case, we can calculate the delta T by finding the mass of this entire system, which we can do. We can find the mass, so we can find the delta T. What we do need is a heat transfer coefficient. So the heat transfer coefficients are kind of locked inside this particular graph. So the heat transfer coefficients are locked in this graph, and what we need for this graph is actually the temperature rise, T minus T infinity. And of these, there is a particular temperature rise that we're looking out for, and that is T max. So T max minus T infinity is what we would need to iterate for this kind of problem. And why 200 degrees Fahrenheit, I am not sure. They basically just decided to use it. Whichever delta T that you use, T max minus T infinity, you will get to the solution eventually. But Sometimes it's just a matter of luck. Yeah, it's just a matter of luck sometimes. So alright, so now let's find for the heat transfer coefficients of our system. So here we have it easy. 200 degrees Fahrenheit is actually marked out for us, and we just find the intersection to the vertical graph. For the multiplying factor for the forced ventilation, we just find 25 feet per second in this graph, and we get a particular value. The neat thing about the multiplicative factor is that it doesn't change with the temperature rise. So what you get here, you no longer have to iterate. Every point of iteration at this point will actually be here. All right. So if your eye is actually good, you will get these values. And when you notice here, that oh, it's so the the number of significant figures is so small. Actually, I think in Shigley, these are in two significant figures. They're 3.0 e raised to negative 6, and it's 2.0 e negative 6. So, okay. I believe for the units decimal place is actually the limit of what you can guess for this kind of graph. So at most you only get two significant figures out of this. This will become important later, but let's continue with our solution. So right, given this, we can solve for that h with the stroke. That is basically this. This is 12.6. Don't forget the 10 raised to negative 6 because it will cause problems for you later if you forget this. All right. So now that we have this, we can actually go by this in essentially a plug and play matter. So we continue to solve for quantities that we can solve until we reach T max. So the first thing that we can solve aside from any thermally related equation here is the mass of the disk. So the neat thing here is that the disk itself is just a very short cylinder. It's just a circle extruded by a fourth of an inch. So you just recall the equation for the volume of a cylinder, then you multiply it by the density. That is the mass of your system. All right. So next, all right. So we have our mass now. The next thing that we can calculate is the energy dissipation. So if you recall, we do have an equation for the energy dissipation. It's this one. So you just plug the given value of the mass inertia from our problem. Our initial omega is 250 RPM and our final RPM is 0. So if we go back here, we will get 10.6 British thermal units. Now, okay, so that is the second one. Um, we can actually go through this in any order that you wish. But I believe the first thing that you have to solve for is the mass itself. Because beta and delta T will not be solvable unless you have it. All right. So, here's the problem. I believe I forgot to include C sub P here. So I'm gonna write C sub P here. It's actually missing, but it should be here. C sub P for this case is 0.108. 0.108, whichever its units are. So yeah, as you can see, I am not really a British units kind of person. Let me just double check what we have. So CP is 0.108. So I'm correct. It's 0.108 British thermal units over pound mass Fahrenheit. So yeah, that's what's missing. All right. Yeah, all right. So now we can actually solve for beta. So beta is just this one times the area, 50 square inch. over the mass here times CP, and that is this. If your beta is actually greater than 1, then you might have an issue. Beta is usually less than 1. Um, if it's not less than 1, you know that you probably forgot 10 raised to negative 6 for this case. Right. So delta T is just from MC delta T. That is 49.3 degrees Fahrenheit here. For this case, delta T does not really change because it's only dependent on the mass and the specific heat of the break. And it's also dependent on the heat dissipation, which it itself is not really reliant on the heat transfer coefficients. All right. So T max is actually the culmination of all of this. So if you take them all together, let's just look at the T max one last time. Okay. So we have delta T, we solve for beta. Now we get T max. So T max is this. And if you subtract delta T from T max, you get this. Now, so this is our 0th iteration. Let's check if it's close to our guess. So Tmax minus T infinity, 209 minus 70 degrees Fahrenheit, that is 139 degrees Fahrenheit. So you have to iterate again. So I've tested this. At most, you'll get there in 3 iterations. Now, here's where the significant figures of our graph kind of matters. So if you look at our graph again, at most, we can only guess by a unit's decimal place. So we can only guess at 2.2, 2.5, 2.6. So at most, 2 significant figures. So that means because we're kind of guessing the value of our H's, we kind of have to appropriate the number of sig figs for our answer. So Tmax and Tmin in this case would only have at most 2 significant digits. And you might be able to get, let's say, 217 degrees Fahrenheit or 167 degrees Fahrenheit for Tmin. But because you're really just guessing the value based on a visual graph, you kind of have to play it safe and use 2 significant figures. So this is close enough to the answer. This might not be the exact temperature, but at least it is kind of reasonable based on the guesstimate that we did. All right. So you might be wondering, why did we mention dry sintered metal? So I believe dry sintered metal actually contains T sub P in this case. You can kind of check in Shigley, the Shigley handout. But there is also another significance. The dry sintered metal has a maximum temperature tolerance that is around 600 degrees Fahrenheit. And for this case, it is safe to use sintered metal for this application. And fun fact, sintered metal is actually, it has the highest, one of the higher tolerances in terms of temperature and pressure among braking materials. So yeah, that is the example problem. So now we've talked about the brakes and how they dissipate. Now we're going to talk about the discs in the brake disc, disc brakes essentially. So again, the disc brake is named after the brake disc and not the braking system itself. The caliper brake system is named after the braking system, which is essentially a sector of a circle that is pressed onto a brake disc. So there are several heat dissipation strategies for brake discs. The first one involves having a space in the middle of your disc. So you have two solid disc pieces, and they're kind of joined by a kind of ribbed structure. So this is from the side of three brake discs, and this is what a cutout looks like. So inside the hollow segment, there are these ribs, and they kind of help facilitate the flow of gases and fluids away from the brake setup, and they also kind of help with the heat dissipation, especially the convective heat dissipation, and we call these ventilated disc brakes. So if there are disc brakes or brake discs with hollow insides, that means there are completely solid disc brakes. So, okay. So, perhaps you might be interested in replacing your solid disc brakes in your car with ventilated disc brakes. So, be careful of that because most of the time, vented brake discs are thicker than solid brake discs. So, that means you not only have to replace the disc, but you also have to replace the braking system that pinches at the brake disc. So that's the first strategy. The second one is more apparent, and that includes boring holes or cutting slots into the brake disc. And most of the time, these are combined. Ventilated discs can have holes or slots in them. For bicycles and motorcycles, it's just one solid disc, but there's a lot of holes and slots in this case. So this kind of strategy essentially does the same thing as vents in a ventilated brake disc. However, they do have the added benefit of allowing dirt or particulates to escape the contact surface between the caliper and the disc so that your operation, your regular operation isn't hampered by dust suddenly collecting in unwanted areas. So, this kind of strategy on its own is more prevalent for motorcycles, for bicycles, and I believe open cart setups. Now, given this, okay, so those are the heat dissipation know-how, hubalu. Let's look at the friction lining material. So when we say friction lining material, these are the parts of the brakes that experience the grueling frictional heat and contact during operation. And there are kind of three basic lining material types. The cheapest one, the most common one is what we call the molded lining. So the molded lining has a solid polymer as its kind of matrix, and it is strengthened by different kinds of reinforcing fibers, along with some additives and fillers, as you can expect from plastics. So these are the least expensive of the lining materials, and it used to be that asbestos was used as the reinforcing fiber. So in case you're not familiar with asbestos, that is actually good because asbestos used to be a health hazard. They didn't figure out it was a health hazard, or rather, there were big companies that were hiding the fact that asbestos was a health hazard. Uh, Asbestos, if you want to imagine what they are, these are kind of rock fibers. So if you can mine wool-like fibers from the ground, that is asbestos essentially. So it's kind of like a rock wool essentially. And this is a hazard for your lungs. Fortunately, these are no longer being used, and there are safer substitutes in this case. The second type of lining material is the woven or the braided lining. If you've seen the Pelton turbine and the Francis turbine setup in the Amped space, this is what it's made of. The woven lining is quite flexible. It's the most flexible out of the lining materials, and it's also the most rugged against dirt and water and rain. So you tend to want to use woven linings for very open setups, so like agricultural setups and whatnot. Now, the last one and the most performatively great lining material is the sintered lining. So, sintered lining refers to this manufacturing process wherein you kind of have metal powder and you kind of force this metal powder into a mold and you use heat to fuse those metal powders together into a solid body. Now, this method of forming metals allows you to have more complexity with less waste. Unfortunately, the resulting metal part isn't as strong as a subtractively manufactured part, but it does what it kind of does its job. And because of the process, you can kind of include other filler materials. Sometimes you can include ceramics, especially high temperature refractory ceramics that enables the high temperature tolerance, high pressure tolerance of these kinds of linings. So overall, these are the stats of these three general lining materials, and although there is some of them are stronger in some properties than others, but you can kind of see a trend for the maximum pressure and the maximum temperature. The woven lining is the weakest in its tolerance for pressure and temperature, and the sintered lining is the strongest in that regard. Now, these linings, depending on the application, you can kind of use them in a quote unquote wet or lubricated manner. So essentially, your brake pads or your linings are immersed in fluid. The problem is, okay, why would you do this? Why would you subject your brake lining to fluid when you know very well that a wet surface has much less friction factor than a dry surface. So the first reason why you would use this is because the oil or the fluid itself helps keep the material cool. So it stabilizes the temperature of your brake setup. That is the main reason. Now, using wet setup or lubricated setup doesn't really affect the maximum tolerable pressure and the temperature of the brakes. So, while it is better for heat dissipation, you still have the question of, okay, so it's kind of weak in terms of friction. What can we do? So, instead of just using one pair of braking surfaces, you just multiply the braking surfaces. That's why that is where you get the multi-plate clutch setups for transmission. So like yeah, you have 2 to 3 pairs of clutch material, and most of the time those are submerged in oil to keep them kind of in a stable temperature. Right. So in Shigley, there is also this particular graph that records the amount of surface area to exert a particular amount of braking power. When it comes to this, there are three kinds of duty cycles here. There's the infrequent cycle wherein they're just kind of used for emergency brakes. Um, I am not sure if car brakes, vehicle brakes fall into this category. The next stage is the intermittent one, as in these are when you expect a stop and go operation, but it's a lot more consistent. Like um it happens frequently more frequently in a period of time. So think elevators, escalators, and whatnot. And the most instance is the heavy duty application. So these are kind of construction types or manufacturing types of machines, and there is a clear trend. So for those that require more area, the brakes that require the least amount of area are actually the drum and the band brakes. So these can exert quite a lot of brake power, even though there's a lot less contact. And this is followed by the caliper style disc brakes. So these are disc brakes in our lecture, but for some they call these caliper brakes. And the brakes that require the most amount of area for the same amount of braking power are the plate clutches, or for this case, Shigley calls them the plate disc brakes. And that is it for friction elements. And thank you so much and have a great day.